Ugh, chemistry. Like, what's the deal? Why is it so hard to wrap your head around it? Is it magic? Well, kinda, but not really. Unless you count the magic of matter, which is pretty mind-blowing if you ask me. I mean, who needs magic tricks when you can just make molecules disappear into thin air? Or your neighbor's backyard. Okay, maybe that's not exactly how it works. But have you ever stopped to think about what makes up, well, everything? From the air we breathe, which, let's be real, is basically just a bunch of gases getting along, to the phones we can't seem to put down. It's all made up of matter, and that's where chemistry comes in. The ultimate detective work. Chemists are like the Sherlock Holmes of the science world, trying to solve the mysteries of matter. They're all about studying atoms, compounds, chemical reactions, and chemical bonds to figure out the properties of matter, its structure, and how it interacts with other matter. It's like trying to solve a giant puzzle, but instead of pieces, you've got atoms and molecules flying around. And let's be real, it's way more fun than solving a regular puzzle. Unless you're one of those people who actually enjoys doing puzzles, in which case, more power to you. Now, chemistry's got a bunch of branches, kind of like a big old family tree. Let's meet some of the relatives, shall we? Firstly, let's talk about organic chemistry. It's like the life of a party, and carbon is the guest of honor. I mean, who doesn't love a good carbon-based compound? Organic chemists get to study all sorts of cool stuff, like organic reactions, the structure and properties of organic molecules, polymers, drugs, or fuels. It's like being a master chef, but instead of whipping up a mean souffle, you're cooking up new compounds. And then there's inorganic chemistry, the metal head of the family. Just kidding, kind of. Inorganic chemistry is all about compounds that don't contain carbon-hydrogen bonds. It's like the cool, edgy cousin of organic chemistry. Inorganic chemists get to study all sorts of fascinating stuff, like ionic compounds, organometallic compounds, minerals, cluster compounds, and solid-state compounds. It's like being a geologist, but instead of studying rocks, you're studying the building blocks of matter. Now let's talk about analytical chemistry. It's like being a super sleuth minus the cool detective hat, although that would be pretty awesome. Analytical chemists are like the CSI team of the chemistry world, using fancy tools like spectrometry, chromatography, and electrophoresis to solve the mysteries of matter. They could be referred to as the chemistry equivalent of Sherlock Holmes, but instead of solving murders, they're solving the secrets of the molecular world. And then there's physical chemistry, the ultimate mashup of physics and chemistry. It's like taking two of your favorite foods, pizza and sushi, and combining them into something entirely new and amazing, although that might not be the best culinary idea. Just imagine the sauce stains. Physical chemists use thermodynamics and quantum mechanics to understand the behavior of matter at a molecular level. Just like being a master builder, but instead of blocks, you're working with atoms and molecules. And finally, let's talk about biochemistry. Biochemists are like a master chef, whipping up a storm in the kitchen. But instead of flour, sugar, and spices, you're working with the building blocks of life itself. Biochemists are the ultimate kitchen wizards, combining the precision of chemistry with the complexity of biology to unravel the secrets of life. Biochemists are usually tasked with figuring out the intricate chemical processes that occur within living organisms. It's like trying to crack the ultimate recipe, the one that makes life itself possible. From the intricate dance of molecules within cells to the majestic sweep of ecosystems, biochemists get to explore it all. They get to explore the fascinating world of proteins, nucleic acids, carbohydrates, lipids, and other biomolecules. But have you ever wondered what makes up those biomolecules? Like, what's the secret ingredient that gives them their unique properties? To answer that, we need to dive into the world of atomic theory. Atomic theory has been around for centuries, with ancient Greeks like Democritus, who proposed that matter is made up of tiny, indivisible particles. Fast forward to the 19th century, and we have John Dalton's atomic theory, which states that elements are composed of small, indivisible particles called atoms. Today we know that atoms are made up of even smaller particles called protons, neutrons, and electrons. Protons and neutrons reside in the nucleus, while electrons orbit around it. This modern atomic theory has helped us understand the behavior of atoms and how they interact with each other. So, what exactly makes up an atom? Firstly, let's talk about protons. Protons are those positively charged party animals that live in the nucleus of an atom. They're like the life of a party, determining the element of an atom and making each one unique, like a snowflake. And then there are neutrons, the neutral ninjas that sneak into the nucleus and hang out with the protons. They're like the quiet, mysterious types with no charge, but still managing to make a difference by varying in number and creating different isotopes of the same element. Electrons, on the other hand, are like the energetic, attention-seeking extroverts of the atomic world. They're negatively charged, orbiting the nucleus like they're in some kind of atomic dance party. And the fun fact is, the number of electrons in an atom is equal to the number of protons, which determines the chemical properties of an element. Now, let's talk atomic numbers and mass numbers. The atomic number is like the atom's ID card, uniquely identifying the element and its position in the periodic table. And the mass number, that's like the atom's weight, calculated by adding up the protons and neutrons in the nucleus. Having explored the fundamental principles of atomic theory, let's now turn our attention to a more nuanced aspect of atomic structure: electron configuration. This concept is crucial in understanding the arrangement of electrons within an atom and how this arrangement influences the atom's chemical properties. Imagine the electrons in an atom as a bunch of rowdy roommates, each trying to find their own sweet spot. That's basically what electron configuration is all about. In electronic configuration, the electrons in an atom occupy specific energy levels, or shells, which are further subdivided into orbitals. The electrons' arrangement within these orbitals determines the atom's valence electrons, which in turn play a critical role in chemical bonding. As we dive deeper into the wonderful world of electron configuration, here comes this loud music in the background that needs to be heard by everyone. For you to be a pro in electron configuration, you've got to be a periodic table ninja. I mean, who needs to know their friends' phone numbers when you can recall the atomic numbers of elements like a boss? But seriously, mastering the periodic table is a crucial step in understanding electron configuration. And if you're feeling overwhelmed, don't worry, we've got your back. If you're looking for a simpler way to learn the periodic table, let us know in the comment section below, and we'll create a video that'll make learning the periodic table a breeze. Deal? Now, let's talk about energy levels, which are also referred to as energy shells. These are the primary divisions of an atom's electron cloud, and each shell has a specific capacity for electrons. Think of it like an intricate puzzle, where each electron is trying to find its perfect fit. But here's the thing, each shell is further subdivided into orbitals, and that's where things can get really interesting. The arrangement of electrons within these orbitals determines an atom's valence electrons, which are basically the key players in chemical bonding. Now, you might be wondering, how do I even write an electron configuration? Well, it's actually pretty straightforward. First things first, you need to know the atomic number, Z, of the element you're working with. Think of it like knowing the secret code to unlock the electron configuration. This number tells you which element you're dealing with, so make sure you've got it right. For example, if you're working with oxygen, the atomic number is 8, which means you're dealing with oxygen's unique electron configuration. Now, let's start filling in those electrons. We begin with the lowest energy level, or period, which is like the ground floor of our atomic apartment building. The first energy level can hold up to 2 electrons. So if you've got an element with 2 or fewer electrons, you're done. But if you've got more electrons, don't worry, we've got more rooms to fill. Within each energy level, there are subshells, S, P, D, F, which are like the different rooms in our atomic apartment building. We fill these subshells in the correct order, S, P, D, F. Think of it like a game of Tetris. We've got to fit those electrons in the right spots. For each subshell, we need to determine how many electrons it can hold. It's like checking the occupancy limit on our atomic apartment building's rooms. The S subshell can hold up to 2 electrons, the P subshell can hold up to 6 electrons, and so on. Once we've filled the subshells, we add a superscript to indicate the number of electrons in each subshell. It's like putting a little flag on our atomic apartment building's rooms to show how many electrons are living there. Finally, we continue filling the energy levels and subshells until we've accounted for all the electrons in the atom. And voila! We've got our electron configuration. Let's try an example with oxygen. We start by filling the lowest energy level, 1Z2. Then we move on to the next energy level, 2s2, 2p4, and that's it. Our final electron configuration for oxygen is 1s2, 2s2, 2p4. So there you have it, the thrilling tale of how to write an electron configuration. It's not as daunting as it seems, and with a little practice, you'll be a pro in no time. Before delving in deeper, let's not forget that there are 3 different methods for writing electron configurations, each with its own strengths and weaknesses. They include orbital diagrams, which are basically like mapping out the atom's electron cloud, then the SPDF notation, which is like a shorthand way of describing the atom's electron configuration. And finally, the noble gas notation, which is like a shortcut for writing electron configurations, although only for certain elements. And if you're at the verge of asking which method is best, well, that depends on what you're trying to accomplish. Do you want to visualize the atom's electron cloud? Then orbital diagrams might be the way to go. Do you want to quickly communicate an atom's electron configuration? Then SPDF notation might be your best bet. And do you want to simplify your life when writing electron configurations for certain elements? Then noble gas notation is the way to go. Now, we'll have to take a tour to take a closer look at the different types of orbitals. There are 4 main types, the s, p, d, and f orbitals. And each type of orbital has a unique shape and can hold a specific number of electrons. So, let's start with the s orbitals. These are spherical in shape, and they can hold a maximum of 2 electrons. They're the simplest type of orbital, and they're found in all energy levels. But what does it mean for an orbital to be spherical in shape? Does it mean that the electrons are just floating around in a sphere around the nucleus? Actually, it's a bit more complicated than that. The s orbitals are symmetrical around the nucleus, and they have no nodal planes. The s orbitals are the simplest type of orbital, and they play a key role in determining the atom's chemical properties. But there are 3 other types of orbitals, and each one has its own unique shape and characteristics. So let's move on and explore the p orbitals. What are they like? How do they differ from the s orbitals? The p orbitals are the dynamic duo of atomic orbitals. Shaped like dumbbells, these orbitals have 2 lobes on either side of the nucleus, and they're capable of holding up to 6 electrons. Found in the second and subsequent energy levels of an atom, p orbitals play a starring role in forming chemical bonds and hybridizing with other orbitals to create new and exciting molecular structures. They also have a nodal plane perpendicular to the axis of symmetry. And if you're wondering what nodal planes are, a nodal plane is essentially a plane where the probability of finding an electron is 0. It's like a line of demarcation where the electron's probability wave function goes to 0. But does that mean that an electron can't exist in that plane? Absolutely yes. The electron's probability of being in that plane is 0, so it's not likely to be found there. But here's the thing, an electron can still exist on either side of the nodal plane. It's just that the probability of finding it in that exact plane is 0. The p orbitals, for example, have one nodal plane that runs perpendicular to the axis of symmetry, and that's what gives them that characteristic dumbbell shape. The electrons in the p orbital are more likely to be found on either side of the nodal plane, which creates that distinctive shape. So, nodal planes are an important feature of atomic orbitals, and they play a key role in determining the shapes and structures of the orbitals. And that, in turn, affects the behavior of the electrons in the atom. Now, let's move on to the d orbitals. The d orbitals are 4-leaf clover-shaped, and they can hold a maximum of 10 electrons. The d orbitals are found in energy levels starting from N3, and they have 2 nodal planes perpendicular to the axis of symmetry. Yeah, that's a lot of nodal planes. But what does it mean for the electrons? Well, it means that the electrons in the d orbitals have to navigate around those nodal planes, and that affects their behavior. And that's why the d orbitals are so important in determining the chemical properties of certain elements. Finally, we've got the f orbitals. These orbitals are characterized by intricate shapes and multiple nodal planes, which create a challenging environment for electrons to navigate. It's just like a 3-dimensional puzzle, where electrons must find their way around 3 nodal planes perpendicular to the axis of symmetry. This requires a high degree of adaptability and flexibility, as electrons must adjust their behavior to accommodate the complex geometry of the f orbital. In spite of their complex shapes, f orbitals can accommodate a remarkable number of 14 electrons, making them a crucial component of the atomic structure. Found in energy levels starting from N4, these electrons occupy a unique position in the atomic hierarchy, influencing the chemical properties and behavior of the atom. The electrons in F orbitals are like the secret agents of the atomic world. They're part of a highly specialized and intricate system, where their behavior is shaped by the complex interplay of nodal planes and orbital geometry. It's just like they're navigating a high-stakes obstacle course, dodging nodal planes left and right, and that affects their behavior big time. After all, when you're an electron in an F orbital, you've got to be ready for anything. And that's why the F orbitals are so important in determining the chemical properties of certain elements. They're the ultimate atomic acrobats. But wait, are you thinking what I'm thinking? What happens when those electrons meet new friends from other atoms? That's where chemical bonding comes in. Chemical bonding is the process by which atoms share or exchange electrons to form a chemical compound. It's like a delicate dance, where atoms move in perfect harmony to create something new and exciting. Let's start with the basics. Atoms are like the Lego bricks of the atomic world. They're the building blocks of everything around us. And just like Lego bricks, atoms have different shapes and sizes that determine how they fit together. When atoms interact with each other, they can form different types of chemical bonds. It's like a menu of atomic options. Do you want to form an ionic bond, a covalent bond, or maybe something a little more exotic, like a metallic bond? Ionic bonds are like the ultimate power couple of the atomic world. They form when one or more electrons are transferred from one atom to another, resulting in the formation of ions with opposite charges. It's like a cosmic game of atomic tag, where one atom chases another to form a connection. Covalent bonds, on the other hand, are like the atomic equivalent of a long-term relationship. They form when two or more atoms share one or more pairs of electrons to achieve a stable electronic configuration. It's like a delicate dance where atoms move in perfect harmony to create something new and exciting. Metallic bonds are like the atomic equivalent of a big, happy family. They form when a large number of atoms share electrons in a sea of electrons. It's like a cosmic game of atomic musical chairs, where atoms move in and out of the sea of electrons to form connections with other atoms. And then there are hydrogen bonds and van der Waals bonds, the atomic equivalent of casual acquaintances. They're like the atomic world's version of a "hello, how are you?" a brief, fleeting connection that's easily broken. So, what determines the strength and type of chemical bond that forms between two atoms? It's quite similar to a complex game of atomic chess, where different factors like electronegativity, atomic radius, ionization energy, and electron affinity all play a role. Briefly, let's discuss some of these factors, starting first with electronegativity. Electronegativity is the ability of an atom to attract electrons towards itself. Atoms with high electronegativity are like the atomic world's version of a diva. They demand attention and attract electrons to themselves. Atoms with high electronegativity tend to have smaller atomic radii. But why is that? Well, think about it. If an atom is really good at attracting electrons, it's likely to have a smaller atomic radius because it's pulling those electrons in tight. On the other hand, atoms with low electronegativity tend to have larger atomic radii because they're not as good at attracting electrons. But wait, you might be thinking, hold on, doesn't a smaller atomic radius mean that the electrons are closer to the nucleus? And wouldn't that make it harder for the atom to attract more electrons? Excellent point. You're absolutely right. However, the key thing to remember is that electronegativity is a measure of an atom's ability to attract electrons in a covalent bond. So, even though a smaller atomic radius might make it harder for an atom to attract more electrons in general, it actually makes it easier for the atom to attract electrons in a covalent bond. And finally, you might be wondering, okay, got it. But what about atoms with really high atomic radii? Are they just really bad at attracting electrons? Ha! Not exactly. Atoms with really high atomic radii tend to be the noble gases, which are actually really good at resisting the attraction of electrons. They're like the atomic world's version of a fortress, really hard to penetrate. Now, let's go in for another factor, ionization energy. What is it exactly? Ionization energy is like the atomic equivalent of a security system. It's the energy required to remove an electron from an atom. Atoms with low ionization energies are like the atomic world's version of an open book. They're easy to get to know and form connections with. And finally, let's talk about electron affinity. What's that all about? Well, electron affinity is like the atomic equivalent of a welcoming host. It's the energy released when an electron is added to an atom. Atoms with high electron affinity are relatable to the atomic world's version of a social butterfly. They're always eager to form new connections and add new electrons to their collection. Wondering why chemical bonding is important? Let's say chemical bonding is like the atomic equivalent of a big hug. It brings atoms together to form something new and exciting. Chemical bonding is essential in various fields, including materials, science, biochemistry, pharmacy, and environmental science. In materials science, chemical bonding is like the atomic equivalent of a master builder. It helps to create new materials with unique properties. In biochemistry, chemical bonding is like the atomic equivalent of a puzzle piece. It helps to create complex biomolecules that are essential for life. In pharmacy, chemical bonding is like the atomic equivalent of a recipe book. It helps to create new drugs with unique properties. In environmental science, chemical bonding is like the atomic equivalent of a detective. It helps to understand environmental processes and solve complex problems. And with that, it's a wrap, guys. We've covered a lot of ground in this video, from the intricacies of atomic structure to the fascinating world of chemical bonding. We've explored certain parts in the periodic table, delved into the world of electrons and orbitals, and even touched on the importance of chemical bonding in different science fields. Now, we want to hear from you. What did you think of this video? Was there a particular topic that sparked your interest? Do you have any other topic that you'll like us to make a video on? Let us know in the comments below. Lastly, don't forget to support us by subscribing to our channel, liking and sharing this video with all your friends and family, or even your enemies. We won't judge. Ha! Thanks for watching, and we hope you had a blast exploring the wonderful world of chemistry with us.